Okay. All right, so today we start calculus. So it's what this course is generally referred to, even though it's technically called calculus of vectors. We start calculus today. And calculus is one of the founding disciplines. Well, I don't want to say the founding disciplines of mathematics, but discipline of mathematics that sort of is popular. Lots of people hear about calculus. And the reason is because it talks about so much that's necessary out in the real world, and allows us to do a lot of, go a lot further than maybe we would in high school. In high school, we studied functions. So you started in grade 9 by studying linear functions. In grade 10, you studied quadratic functions. In grade 11, you started talking about cubics and rationals and root functions and all sorts of other ones. And then we even took advanced functions at the beginning before coming to this, where we talked about even going deeper with those functions. When we get to calculus, calculus describes how those functions behave. So you'll see it in the example we're going to do today. We've often studied a function that gave us one sort of output. What we're going to study in calculus is how that output changes. So a good example I like to use is if you consider a bridge, and I'm sure we've seen bridges like this, where it's like that, and you've got a parabola as the supporting part of the bridge. So the bridge goes along the top, and all the supports are in a parabolic shape. So that's what we've been studying is the shape of that parabola and where all the positions are on that function. But in real life, the parabola doesn't just stay still. We try to keep it staying still when you're building a bridge, but there are so many things that change. And as trucks drive across the bridge or cars drive across it or nothing's on it, everything's changing. And how these functions change is probably more important than where they are when they're stagnant, because very few times are they actually stagnant. So we're studying how functions change. And if you think back to advanced functions, we finished off by talking about the rate of change. You may remember back to IROC and AROC, the average rate of change and the instantaneous rate of change. Well, we're going to start right there. And as I said, normally what happens in a semester, we finish advanced functions sort of on a Friday, and then on the Monday, we start calculus. And so this first lesson actually is a continuation of where we left off in advanced functions. Now, it's been a while since we did advanced functions, and so we'll remind ourselves today what those IROCs and AROCs are, but it's all about how things are changing as opposed to where they are. Okay, it's all about changing functions. And that's something you just keep in your mind when we do things. Okay, so we're going to start by doing a Desmos activity. I'm going to release it now. So you'll go to Classroom. And we're going to go back and forth between the Desmos activity and live. Okay, so make sure you don't put me on mute for too much, because we're going to be going back and forth, back and forth. The Desmos activities are meant to sort of replicate some of the worksheets I would normally give you. Normally this is all in a worksheet, but I've translated it to Desmos so that we can do some of the stuff there. Okay, so you're going to be studying information about a dragster and how the dragster changes. Not just how far the dragster goes, but how it changes. So I'll give you a second to get into Desmos, and I've restricted you to the first, I think, 6 slides. So you'll see there's more slides, but you can only go certain far, because we're gonna stop at 6 slides and come back. Okay, so you can go off and try the Desmos activity. Okay, can I get a mic check?
Yeah, you're good.
Okay, thanks. All right, so yeah, forgive me here. We've got the new setup here, but it should feel pretty much the same for you. It's just I'm broadcasting off of a Chromebook instead of a big screen TV. So I might be coming in and trying to zoom in to see what I'm seeing, but nonetheless, it should work. So I've stopped you on slide 6, which essentially shows the graph that I have on the screen here. Oh, I'm not presenting yet, am I? So. All right. So everything on your end should look the same because I'm still presenting the same way. So I've stopped you on slide 6, which essentially looks like this one here. Of course, this the one on Desmos looks a little bit nicer. But what it asks you to do then is to look at this special secant. So I'll stress this here. We've been talking, normally we would talk about the quadratic function. In grade 10, we would have investigated this. It's 19t squared. So we get the shape of the quadratic function. And the quadratic function talks to you about distance over time. Okay? So it's how far the dragster has gone over a certain amount of time. And that gets in a quadratic shape. But what we're investigating is how that distance changes. So in this particular case, how distance changes is the speed. Now, we've looked at this before when even back to grade 9, where we talked about how some graphs were steeper than others, and that meant that things were going faster. So if it was steeper, the rate of change was faster. In grade 9, we called that the slope, the rate of change. In grade 10, we have the A value as the rate of change. So what we're doing is describing how this shape changes. So if you look at the shape of the quadratic function that's happening here, it's pretty flat at the beginning because it's not going as fast. But as they slam on the acceleration, it goes faster. So the shape of the graph, the rate of change of the graph increases, and therefore the speed does. So what we want to know is how fast this line is changing, this function is changing. That's what we're studying. Not just where the function is, but how fast the function is changing. So if we, and it says, how do these secants or line segments indicate the rate of change? So the steeper the graph is, the faster things are going. And I think that was one of the questions you had to answer. Now, what you were doing in the last slide, and, or sorry, I don't know which slide it was, but on slide 6, you are calculating the slope of that secant, and you're finding the average rate of change. So you're essentially finding the slope of this green line that I have there. I think it's the blue line in Desmos. You're finding the slope of that. And so from back in grade 9, we know the slope is y2 minus y1 over x2 minus x1, right? So here's our, oh wow. Just gotta fix this. So it's y2 minus y1 over x2 minus x1. So y2 minus y1, oops, not y squared, y2, y1 over x2 minus x1. That's the slope formula that we've known since grade 9. So finding the slope formula on this guy goes from here to here, we're finding that. Now, in this particular example, y is distance and x is time. So you can also imagine this function, this description of the slope. The distance that you're at now minus the distance where it began, and over the time now minus the time where it began. Or you can even consider it this way. Because distance is a function of time. And so the y values, distance, is simply a function of the x values with its time. So the distance comes from plugging in a number into the function. And the second distance is found the same way. Now, that's what you did back on the first slide. You went off and did this. So we're looking from 0 to 3 seconds. So we want to know where are we in 3 seconds. So we would go f at 3. Now, you probably just jumped back to your table to figure out that f at 3 was 19 times 3 squared. 3 squared is 9 times 19 is 171. Okay? And so you had that number, so you used it right here, or you used it as your y2 because we knew that this was at 171. So all of these different versions actually mean the same formula. Okay? But I am going to use this one here. So f at 3 minus f at 0, because we're going from 0 to 3, over the change in the time, which is 3 seconds, because we're at 3 and we started at 0 seconds. Now, you might actually, if you had a different function, you might do this math all within this formula. So you might actually do the 19 times 3 squared. And similarly, we had to find the function at the beginning. Well, of course, at the beginning, it's not moving, so there's no distance. But that could be calculated off to the side or actually within the slope formula. So if you calculated it within the slope formula, it would look like this, but of course I know that 3 squared is 9 times 19 is 171, the 0, and 3 minus 0. And of course, 171 divided by 3 is 57. And then what you got and plugged into the calculator was the exact same value. Okay? So that was finding the rate of change of that function. And it says that the average speed between 0 and 3 is 57 meters per second. And that's what we've found so far. Now, what you're going to do in a second on the next slide is look a little bit deeper. So we're going to do this calculation again, but we're going to do it on a different secant. So you don't need to look at that top part because you'll have a different picture on your screen. But we're going to do it 4 more times. And each time you're going to use this idea. Okay, so this time, instead of looking at the first, the interval between 0 and 3, we're going to look further down the graph and look at the interval between 3 and 4. So for each of these, you're going to go f at 4 minus f at 3 over 4 minus 3. So that's for the first interval. Now, that f calculation, again, you already did for the first slide, so you could go back and use it. So if we went back, you would see that f at 4 was 304. So it was at 304 meters minus f at 3, we just did 171 over 4 minus 3 is 1. And we'll get 133 meters per second. So that means the average rate of change between the 3 second and 4 second spot is 133 meters per second, which is not surprising because what we're doing is looking at this secant further on. And the graph, of course, is much steeper at that point. Okay? So that will be your calculation for the first one. You're going to repeat this process, and I need you to get used to doing this because we're all building upon this idea. But you're going to change the interval. You're going to go between 3 and 3.5 seconds. So you're going to need to do a little bit more calculations because I didn't ask you to find the distance at 3.5. 3.1 and 3.01. And we'll plug those in, and I'll come back in a moment. Okay, so your next slide should be open in Desmos. You can head off and do that, fill out this chart in Desmos. Okay, so hopefully you've done those calculations, and I see most of you have moved on to the next slide to start checking those calculations. So let's just have a look at what we have discovered. So here is the 4 calculations, again going from 3 to 4, which we did together, and then try 3 to 3.5, 3 to 3.1, and 3 to 0.01 seconds. And we get down to 114.19 is the average speed between 3 and 3.01 seconds later. So what's going on? So we should all have eventually gotten to this slide, and I'll just put it back. So when we first got here, it was set up with the first secant. And of course, Desmos can do this math. So it calculated the secant for 133 meters per second. And if you look at that blue line, it's a pretty good representation of how steep that curve is at that point. And these secants are all they're trying to do is represent how steep the curve is. Now, because it's a curve, we can't actually use the slope formula on a curve because it curves. Right? So these lines are meant to represent the curvature of the function, the quadratic function, but it can only be a representation. All right. So what we have here then is the slope of this big secant from 3 to 4 seconds is 133. And it's a pretty good representation of what's going on between 3 and 4 seconds. But if you stop and think about it, you can imagine, because it's a dragster going so fast and the acceleration is so quick, at 3 seconds, the speed is one thing, and at 4 seconds, the speed is different. So the average speed is going to be a little bit different. Then what I did was I gave you smaller and smaller intervals. And so the second calculation you did went to from 3 to 3.5. So if I move my cursor down there to 3 and 3.5, the slope of the secant now is 123.5 meters per second. So of course, it's not quite as steep as before because the graph is going up. We're now coming back closer to this 3-second mark. And your math supports what we did up here. Okay, and then going even closer to 3 and 3.1. So, there we go. So now I have a really tiny secant between 3 and 3.1 seconds, and the slope of that guy is 115.9. And then we go even smaller down, oh, perfect, to a secant between 3 and 3.01 seconds. And it turns out that that little secant is 114.19 meters per second. Okay, so we've taken this and we've shrunk it down into smaller and smaller representations of how steep the curve is right around this 3-second mark. All right, so I'm going to open up the next couple of slides, but we're sort of going to do them together. Okay, so we'll go to the next slide here. So we should be over on slide 9 now. And so which interval do you think best represents the actual speed at 3 seconds? So we have a bunch of representations of the speed around 3 seconds. We have one from 3 to 3.3 to 4, 3 to 3.5, 3 to 3.1, and 3.01. So let's see what you think which interval best represents the actual speed. So I'll let you guys answer that and I'll check out your answers. Yeah, good. So we've all figured out, of course, that the smaller the secant, the better a representation is of the actual speed. And then the follow-up question is, yeah, everyone's saying between 3 and 3.01, good. The follow-up question is, how fast do you think the dragster is actually going at exactly 3 seconds? And we can see people answering that question, so I'll give you a second to answer it. Okay, I'm getting some good answers here. Okay, so let's see what people are saying. So everyone has said that the best interval to represent what's actually going on is the 3 to 3.01 second one. And then how fast do you think the dragster is going at exactly 3 seconds? And this is where I see different answers. So this is good. I wanted to hopefully see this. So many people guessed 114 meters per second. Which is a good guess. Some guessed 114.19. We have one guess at 171 and one guess at 57. So let's check out this one. Okay, so we have this secant here. We've already said that the best secant is the one that is the smallest. Okay. If I can get down there, there we go. We have this small little secant from that there. It says which interval is the best. So we all agree that that little secant is the best representation of what's going on. Now, how fast do you think the dragster is going at exactly 3 seconds? Well, we have two options. Carl here has selected this option, 171. So this is going to be a little bit of a heads up, and I'm glad that someone answered this because this is a common answer. We have 2 points going on here. The first one is the black point here, which is actually right on the curve. And it says, since it's on the curve, it is part of this graph. And it says that at 3 seconds, the distance traveled is 171. So the 171 is not the speed. The 171 is how far it has gone after 3 seconds. So it's gone 171 meters in 3 seconds. But the speed is how fast the curve or how steep the curve is at that point. And we've represented it with a small little secant right there. And we said the slope of that curve is roughly, what do we got here? 114. Now remember, when you see this blue thing, the blue part is just the other end point. Okay, it's telling you the distance again. So let's go back to here. It's the distance. So at 4 seconds, it's at 304. It has nothing to do with the speed. The calculations you did is what's important, what the speed is. So you did this, the rise and run, the change in y over the change in x, and we found that the steepness of the curve was 133, and then we got better and better representations, and we got down to 125, and then 115, and then 114.19. And so what we need to do then is make a guess that the actual steepness of the curve at that point is 114, maybe 100, exactly 114 meters per second. I don't know, it's getting closer. Maybe it's 114.1. We're not sure. But we could, if we wanted, go off and figure out the slope of the secant between 3 and 3.00001. That would get it even smaller, smaller, and smaller. But each time the answer, the steepness of that answer is getting closer and closer to the actual speed of the answer of the graph. Okay, and the 57 that someone answered, I think, was going back a couple of slides and talking about the average rate of change from 0 to 3. And I'm talking about the rate of change between 3 seconds. Okay, so we've got a bunch of guesses at 114. One guess at 114.19. Now I would suggest it's less than that because that's the steepness from 3 to 3.01, we want to actually bring it down to exactly 3. So I think it's going to be a little bit smaller than that. We have a guess at 114.1. So let's actually move on to the next slide, which I'll open up to you. So depending on what you answered there, we're going to actually go and drag it so that the point is right at 113. So instead of just a little distance, we're going to put it right at 113. Or sorry, right at 3 seconds. So we're getting down the slope of the secant, getting smaller and smaller and smaller. And we're going to put it right on that. And something happens. So I want you to think about what just happened there, because our slope of the secant says NaN right now, which I can tell you stands for not a number. NaN means not a number. It's like an error. So let's see what people answered. They answered NaN. But I want to know why the Desmos breaks down. So think about that. Okay. So I'm seeing some really interesting answers. Yes. Yes, yes, yes. Okay. Okay. So I think most people have given me an answer to what happens. Okay, just waiting on Shihako Ishii. Hello, Shihako. Okay, let's talk about what's happening. Okay, so I paused you. Maybe I would pause you in the middle of a sentence, and I apologize for that, but I want everyone to come back to the Google Meet so you can see me presenting the screen so that I can explain what's going on. Okay, so we'll use Gene Springer here as an example. So what we're trying to do is find not an average rate of change, we're trying to find an instantaneous rate of change. So exactly how fast it's going. The secants can only calculate average rate of change. And sometimes it's good and sometimes it's bad. If I go back to the beginning to this rate of change, this secant is a bad representation of how fast it's going. 57 meters per second isn't really a great representation of how fast the dragster is going throughout this first 3 seconds. The secant here, the blue line, is way too steep to represent the steepness at the beginning because the graph is much shallower. Okay, so 57 is way too high. But at the end, the graph, the red line, is definitely going steeper. And so this blue graph is not steep enough. So this large secant is not a great representation of what's actually the speed at the 3 second mark. And so what we said was, okay, well, let's change that and start shrinking our secant. So this is a pretty good representation of what's going on, but if you look at that blue secant, you can see it's steeper than what's actually happening around this 3-second mark. So, you know, we got 133, but that's too steep. So what we did was shrunk the interval down, 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 down into a really tiny interval right there. That is the best representation that we could come up with on Desmos or in our calculations to say that, okay, the steepness of that secant, that blue graph, is almost exactly the same as the steepness of the red graph. And so we're going to say it's about 114. Some of us guessed, sorry, this was 114.19. Some of us guessed actually 114. But we actually then moved on and said, okay, well, why don't we actually make the secant right on there? And of course, we get this, what happened? So let's see some of your answers. So Mary here says not enough points to provide slope. That's right. In order to find slope, 2 points are needed. Yes. The secant no longer exists. Good. Okay. Remember, a secant is adding or connecting 2 points on the graph. If you put them on top of each other, the secant's not even there. It's not possible. These are great answers. You can't have a slope of 1 point. True. It cannot give us a slope because you'd be doing 171 minus 171 on the top and 3 minus 3 on the bottom, which is also a 0. So what we have is 0 divided by 0. That is not possible. We can't divide by 0. There's no slope between them. You can't have 0 as a denominator. Very nice, Eugenia Cheng. Okay, there's no slope. Okay, everyone's sort of getting the idea. Now it is the IROC, I agree, but we can't calculate it because when we shrink our secant down to a single point, then we lose the ability to calculate slope. So this is one of the major fundamental problems that happened that needed a calculus solution. And the way we figure out this problem is one of the fundamental theories of calculus. That's why it's so important that we stop and look at this. All right, so how do I find the slope at a single point? Well, let's just go one step further. So I'll unpause this and go to one more screen and get you to imagine that instead of finding a slope, you would find a tangent. Or sorry, instead of finding a secant, you would find a tangent. And so if you've dragged the dragster to the exact 3-second mark, Desmos will tell you the slope of the tangent is 114, which is what many people guessed. And we kind of saw that it was getting really close to 114. So we got it down actually to 114.19, I think. But if we kept shrinking the secants down to one spot, if we could calculate it, it would tell us the answer is 114, and which is what many of you had before. So again, I'm going to pause the Desmos activity to make sure you come back to the Google Meet so that we can really talk about this idea. Okay, because this idea is what's the fundamental idea of calculus. All right, so our goal here is to try and figure out how steep the curve is at 3 seconds. Secants are really good representations, but all they can be is representations. but at least we can calculate the slope of secants because we have 2 points. You and I right now don't know how to calculate the slope of the tangent because the tangent only has 1 point. So our slope formula breaks down. But Desmos knows calculus, so it knows how to actually figure it out. And it found out the actual slope of this tangent was 114 meters per second. So if we could take the secants and shrink them infinitely small, we would get 1 point. And if we can imagine that it's infinitely small and we could actually calculate the slope of the tangent, that would be the infinitely small secant that's represented here. We would find the slope of the tangent is 114. Now, until we learn calculus, we can't do what Desmos knows, or we can't do what Desmos does here. All we can do is estimate how close we can get and get a pretty good estimate by shrinking that interval down so it's so small that it's essentially about the same size as the tangent, okay? That concept is really valuable. The challenge that we're going to spend the first few days of calculus doing is figuring out how we can actually figure out the slope of this tangent, given that we can't find slope of 1 point. That's going to be our hurdle that we have to get over. Now, if you look more at the tangent that's on the screen here, you can see then now this really represents exactly how steep the curve is at different spots. Again, it's not telling me where the dragster is or how far it's gone. It's telling me the slope of the tangent, which is the speed. And so when we go back to the beginning, obviously the slope is 0 because the car is not moving. So the curve is at 0. But as soon as it starts to move, you see the speed going up. And you see here at 1 second, the speed or the slope of the tangent is 38. Remember we guessed the speed was 57 in that first secant? Well, that's not a great representation for what's actually going on at 1 second. It's 38. And then, of course, as we go along here, you can see at 2 seconds, it's way more than that secant. It's 76. And when we get to 3 seconds, we find it's 114, which is an awful guess. Or that's where our secant is really bad because we were guessing it was about 57. Well, it's not. It's definitely that. And then, of course, as we get faster and faster, the steepness of the tangent, just like the steepness of the curve, increases to a point where we're going 190 meters per second at the 5 second mark. Okay? All right. So we'll open up the next slide and do this one again together. So go back to Desmos. You can just listen to what we're doing here. So a secant, this sort of summarizes what I just said. A secant can estimate the IROC by calculating smaller and smaller slopes. We can calculate the slopes of secants, but right now there's only 1 point, which would mean we'd be dividing by 0. So that's why when you're calculating the secant, it's not a number. But if you could figure out a tangent, the tangent would be the best representation. But we don't know how to find the slopes of tangents yet. So we'll have to rely on Desmos for a couple of days before we figure out how to do that. And so then we get down to slide 13 now. Oh, I've paused it, haven't I? Sorry. There you go. So you can scooch through. You maybe just watched me with that summary of slide 10. So then we get down to slide 13. So again, we're going to kind of do slide 13 together. So if we want to estimate the IROC at 1 second, what we would do is shrink our interval down closer and closer to this 1 second. Right now, the secant you see on my screen is not very good. So we're going to shrink this down closer and closer and closer. If I go down to 1 second, okay, again, remember the coordinate is not telling me speed. The coordinate is telling me distance. However, it kind of matches here. Okay, so drag the blue point on the secant to see smaller and smaller intervals. I think the actual graph started at 1. Yeah. So if we shrink this down smaller and smaller and smaller, you can start to see that the secant is doing a pretty good job at estimating it, but not exactly right. So you in your head are probably estimating about how steep the secant is. I'm going to get a secant. Oh, I can't get it right on there. I'll go from 1 to 1.02 seconds, and it says the steepness is 38.3 meters per second. I can see it's getting smaller and smaller, getting closer and closer. I can even go on the other side of the point and get secants coming from the other way. Okay, so I'm going to guess, just seeing that it's about 38 is going to be my guess. And then when I click on the secant, you can see exactly that the slope of the tangent is 38. Okay, so this is the math we're going to do here for the next couple of days, is estimate smaller and smaller secants until we can get a pretty good estimate of what the tangent is, and then we'll ask Desmos, how was our guess? Was it close? And that's where we're moving towards. So then I've opened up your Desmos activity to the next one. And we are then just going around and playing on slide 14. We're just playing with the different stuff, okay? And what I want you to see as you're moving along is recognizing that I'm telling you 2 bits of information. I'm telling you the speed, which is the slope of the tangent, at 3 seconds. So that's the second part. Because it's not just what the speed of the dragster is. The speed is different at different times. So when we're talking about the speed or the slope of the tangent, we have to not just tell how steep it is, but where this calculation is happening. Okay, now I'm going to pause the activity again and ask you to come back to our screen, the Google Meet, so you can see what I'm doing. All right, so I've moved on, even though you can't move on yet. That's okay. I've moved on to our second problem. So instead of investigating the speed of a dragster, we are calculating the growth of a bacterial culture. So it's a different function. The dragster was a quadratic. This is a cubic. Now, bacterial functions can also grow exponentially, but we're not going to do exponential ones. We're going to just look at this cubic, which is a pretty good representation of what's going on. And we're going to examine that. Now, this is where you're going to be going in a moment. So you're going to redo the same calculations by hand at different intervals, getting used to this new function. Okay, so plugging in new bits into the new function and then spitting out the AROCs. Okay, and then you're going to check your answers just like we did before by taking different secants. This time it's not a dragster, it's represented by this. And again, stressing, this number tells you how many bacteria. We want to look up here to find the slope, because that tells me how fast it's changing. You'll go off and try this. Now we're going to estimate at 4 hours. So I want you to imagine what you're going to do at 4 hours. Do the calculations for all these sort of stuff. And then you're going to estimate what you think the rate of change is exactly 4 hours. And you see these intervals are before 4 hours. The other ones we were doing after. That's okay. And then you'll check your answers and see how good a guess you had in your work. Okay? All right, so what I'm going to do here is set you off to try the next set of practice questions. You've got one on bacteria, and then there's one later on. And I'm going to give you that plus a little break here, and we're going to come back together at around 10 o'clock. So you're going to probably need about 10 minutes to finish this activity, and then 10 minutes to stretch your legs. Actually, let's make it 5 to 10. Yeah, so at 9:55, we'll come back and I'll let you go off and try the rest of this Desmos activity. Any questions? Okay, so I will see you at 9:55. So I've opened up the Desmos activity so you can keep going. Oh, but I gotta open up how far it goes. 1 second, sorry. All right, there you go. So now it's opened up. So spend about 10 minutes finishing the Desmos activity, 10 minutes taking a break, and we'll see you at 9:55.